Okay, so today we're going to talk about one of the basic or fundamental concepts of calculus, which has to do with limits. So we're going to be finding limits of functions. So the concept, so let's kind of briefly, before I define what a limit is, let me kind of talk about the conceptual idea behind the limit. So the concept of limits is to determine which value a function goes to as we approach and when I say approach, see, we notice that we're getting close to something. And anytime we approach or we talk about limits, we're talking about from both sides. Okay, so this is a two-sided limit. And in fact, all limits are two-sided unless we're told otherwise. So as we approach a specified value, and see the specified value that we approach, we're basically saying, I don't care what this function is at that value. Okay, we care more about as we approach it. So in other words, we do not care what it is at that x value. So usually if we're talking about the specified value is some x value that we're getting close to, but we don't care what it is at that value. Okay, so let's define this, and then we'll go from there, and we'll see some visuals as to how this works the way it does. Okay, so but remember, like I said, the concept is to determine what y value my function approaches or goes to as we approach some specified x value. Now, whether it's defined at that value or not, I could care less, because as I'm getting close to that value, I'm never really at that value. Okay, so by definition, here's what we have. If you write the limit as x approaches a of f of x, this equals to L, which is basically what we were just talking about. So if you notice, here's what we're saying. So if we were to translate this, so this basically means, and if we were to translate this, the limit as x approaches a from both sides of a equals L. And maybe I also need to add in here, when we say the limit of what function, and the function that I'm finding the limit of is f of x. So maybe I should add in here the limit of f of x. Okay, so basically we're saying as x gets really, really close to a from both sides of a, this function takes on the y value of L. So basically that's kind of what the definition of a limit is. So to kind of use notation, like instead of writing it this way, we could say the following. Look, as x gets close to a, what is it that we know? F of x approaches capital L. So that's kind of like what we're saying here. So let's look at our first example. We're going to say determine the limit, which is defined as the limit as x approaches 5 of 6 over x minus 5. Okay, so right now, the way that we're going to kind of evaluate this limit, which in later sections to come, we'll come up with more effective and more efficient ways of evaluating limits. But the way that we're going to solve this is we're going to use a table. So we will use a table. Okay, and when I'm using this table, just keep in mind that, like I said, in later sections, we'll come up with shortcuts where we'll try to avoid using the table. However, we're not always going to be able to avoid using a table. So there will be certain instances where we have no choice but to use a table. Okay, and there will be some other problems where we're better off using a table, because if we don't use a table, we may get a misleading answer. Okay, so for now, let's actually create a table of values and let's see what happens to this function. So what I'm trying to do is I'm trying to see, look, as x gets close to 5, what does 6 over x minus 5 do? So let's pick a value. Let's start off to the right of 5, because remember, I need to check both what happens to this function as I approach 5 from the right side and what happens to this function as I approach 5 from the left side. So let's pick 5.1. And I've already done the calculations, but if you plug in 5.1 in here, you get 6 divided by 5.1 minus 5, which is literally saying 6 divided by 0.1, which is 60. Okay? So I still don't see a pattern. So what I want to do is now I want to get as close as I can to 5 and see what happens to my y value. So if I plug in 5.01, I get 600. If I plug in 5.001, I get 6,000. So in fact, what am I noticing here? As I approach 5 from the right side, my y values get larger and larger and larger. And so we could see that the right side goes up to infinity, or it becomes infinite. Okay, so hopefully this process looks familiar to you, because in section 1 of this chapter, that's all we did, right? We were kind of indirectly working with limits, right? We were starting at a value, and then we got closer and closer to a specified value. So we hadn't really introduced limits yet in section 1, and so here's what we're basically formally introducing limits. So section 1, like I said, was kind of like a discovery section, where we're discovering a bunch of things, and later on in this chapter, we're kind of going to go and define what we're doing in section 1. So clearly in section 1, we're working with limits, and now here we are defining what limits are. Okay, now coming back to this problem, I've only checked my x values to the right of 5. Now I need to check to the left of 5. So if I plug in another value like 4.9, if I plug in 4.9 here, I get 6 divided by 4.9 minus 5, which gives me negative 0.1. So this becomes negative 60. And if I plug in 4.99, I get negative 600. If I plug in 4.999, I get negative 6,000. And so what do I notice? As I approach 5 from the left side, I get negative infinity. So here's the problem. Does this limit exist, yes or no? Well, let's come back to this definition. For a limit to exist, if I approach a from both sides of a, this function has to go to the same number. Now, if I look at this, what do I notice? From the right side, it goes to infinity. From the left side, it goes to negative infinity. So it's doing two different things, okay? Now, let's not talk about what happens to infinite limits, or what happens to my function if it goes to infinity. Does it exist or does it not? Because we'll talk about that later on in this section, or in this notes. It will come later. But what we notice is, since the right side and the left side don't agree, this limit does not exist. So we could say that since as we approach x to, or let's put it this way, since the left side and right side of 5 don't produce outputs that agree, then this limit does not exist. Okay, so for this, I mean, this is kind of extra that I put in here, but once you see that if you approach a number from the left and the right side, and if they don't agree, the outputs don't agree, you automatically say that this limit does not exist. Okay, and so like I said, as far as infinity goes, don't worry about that for now. We'll talk about that later. Okay, so Let's look at another example. So for example 2, if I say find the limit as x approaches 0 of sine x over x. So what am I doing here? My goal is to see what happens to this limit as x approaches 0 from the left side and the right side. So instead of doing these calculations by hand, which are pretty much impossible, we're going to use a calculator to do these calculations, and then we'll see what happens to the limit. So if I go back to this function, and what is it that I want to find out? I want to find out sine of x divided by x, and I want to see what happens to this ratio as x gets closer to 0 from both sides. So if I go to my table, which is right above the graph, so second table, and if I start off with this value. So let's start off to the right of 0. So let's pick a number close to 0. So let's plug in, let's say, I don't know, 0.2. If I plug in 0.2, I get a value of 0.99335. Okay, so let's get even closer to 0. What if I plug in 0.1? I get 0.99833. And then what if I plug in 0.01? Then I get 0.99998. What if I plug in 0.001? I get pretty much 1. So what's the calculator saying? It's not saying it is exactly 1, but we could see that as I'm getting closer to 0 from the right side, this gets closer and closer to 1. Okay? So far, we still can't say that the limit exists because I've so far just checked what sine of x over x gets closer to as I get close to 0 from the right side. Now, to complete this, or to see if this limit exists, I need to check this guy from the left side of 0 to see if it approaches 1 as well. If it does approach 1, then the limit exists. So let's try negative 0.1. So what do we get? 0.99833. If I plug in negative 0.01, we get 0.99998. So what is it that we're noticing? As I'm getting close to 0 from the left side, this function, sine x over x, also approaches 1. So in this case, this limit does exist. So we could say the limit as x approaches 0 of sine x over x, since from both sides it agrees, they both approach the same y value, we could say it's 1. Okay? And so the idea, this one simple idea is actually really cool, the way that it works out. Because if you think of those watches that manufacturers design that don't require a battery and they're just self-winding, they work off of this. The way these manufacturers design those watches, they say, look, count each second in terms of sine x over x. So it's kind of like the angle it makes along with x. So that's why we get this. So what is it that we're saying? If x is a very small angle, then sine of x divided by x is roughly the same number, right? If you think about it, how do you get 1? What this example is stating for us is that sine of x is about the same thing as x when x is near 0. Okay, so this is actually an important concept. We'll see it over and over again. In fact, there'll be different ways that will show that, look, if you're close to 0, sine x over x is 1. Okay, but the way that we showed it today is simply by a table. Okay, so so far the only types of limits we've talked about are two-sided limits, and in fact any type of a limit that you see, unless told otherwise, is always a two-sided limit, meaning that we're approaching a, or whatever the number is, from both sides. Now we also have one-sided limits. Okay, and one-sided limits are actually not as strict as two-sided limits, because I'm sure you can guess we're only interested in approaching a number from only one side of it. So what we could say here is that, look, one-sided limits has to do with what value a function goes to as we approach a, and the keyword is approach, a specified value from one side of it only. So now we're being more specific. It's basically either from the right side or the left. Okay, and so the notation of this will slightly change. Okay, so here's what the definition is basically saying. If we look at this, we could say the definition, the limit as x approaches a, and right above a, I'm putting a negative, which what do you think that negative means? That negative means simply that we're approaching a from the left side, or where x approaches a from the left side of a. So we could say that the limit as x approaches to a from the left side of f of x equals to L. So what does this mean? To translate this, we could say as x approaches a from the left side of a, f of x, what does f of x do? Well, f of x approaches the value L. F of x approaches L. Okay? Let's ignore that. It's approaches. Okay? So then, how do we define a right-sided limit? Which, I'm sure you guys could guess, it would look similar to that, except instead of having a minus above it, it has to have a plus. So remember, if it doesn't have a plus or a minus directly above it, then that means it's a two-sided limit. So if it's one-sided, you'll know, okay? So if they don't write anything, if nothing's written, if you don't see a plus sign above it or a negative above it, then it's a two-sided limit automatically, okay? So this one is pretty much saying the same thing as above. So we could say, look, as x approaches a from the right side of a, f of x approaches L. Okay, so that's basically what one-sided limits look like. Okay, so now let's look at a diagram where we'll kind of put all of this to use. And in fact, once we make this diagram out and I ask these questions, it would be nice if you could just pause this video and see if you could answer these questions yourself, and then you could play it again and see if you got them right or not. Okay, so I'm going to draw just some random function. So we'll call that D, and then we'll call this A. We'll call this a y value of B. We'll call this a y value of C. And so I'm going to just draw some random stuff, something like that. And then we have this. And then we can go down to D. Let's call this y value E. And this goes on like that. And let's call this, let's put a point there, and let's call this F. Okay, so what I want you to do now is I want you to find the following limits. So find the limit as x approaches a from the right side of f of x. We could then say find the limit as x approaches a from the left side of f of x. And we can say also find the limit as x approaches a of f of x. And finally, find the limit as x approaches d of f of x. So this is your function f of x, and find each one of these. Okay, so I would pause the video now and just find them, and then play it once you're ready to see this. So let's talk about these. So what is this saying? If I go to my function f, which this is the function f, what y value does my function approach as my x values approach a from the right side? So here's a. So if I go to the right of a, I'm going to jump up here. So if I approach a from the right side, what do you notice is happening to my y values? They're getting closer and closer to what y value? They're getting closer and closer to c. Notice how what we're saying is, look, I don't care what my y value is at a. I care what happens to my y value as I get close to a from the right side of a. So if I'm to the right of a, I'm up here. So this function actually gets closer and closer to c. Okay, so the limit as x approaches a from the right side of f of x, that's going to be c. Now, what happens to my function if I approach a from the left side? Now, here's a. If I go to the left of a and I start getting closer and closer to a from the left side, what do you notice? Your y value gets closer and closer to b. Okay? However, what do I notice now? This is actually a two-sided limit. So what's the limit as x approaches a of f of x? Now, this is a two-sided limit. I need to see what happens from the right and from the left. But notice I did that up here. So in fact, we could say since I approach a from the right side is c, and since I approach a from the left side of f of x, which is b, and since b and c clearly are not the same value, this two-sided limit does not exist. Why? Because from the left side, I go to b, from the right side, I go to c, which those don't agree. So the two-sided limit doesn't exist. So right away, we can see that one-sided limits are more likely to exist. Two-sided limits are more strict because it has to satisfy two conditions for you to say that this exists. Okay, now let's go back. Now let's go to the last one. What's the limit as x approaches d of f of x? Now look, if I approach d from the right side, my y value approaches, or this function approaches the y value of e. Okay, now what if I approach d from the left side? If I go to the left side of d, I'm along this path, and as I get closer and closer to d, my function approaches the y value e. So notice how from both sides they're approaching y equals e. So this limit actually does exist, and it's e. So the one other question you should ask yourself is, why is this not this last limit? Why is it not f? Why is it e? And the answer to that is, remember, I don't care what my y value is at d. I care what my y values approach as I get close to d. So if I'm getting really, really close to d, this function gets closer and closer to e. Once I hit d, then I jump down to f, but I don't ever care to hit d. I'm just going to get as close as I can to d without really getting there. Okay, so I hope all this makes sense. And if it doesn't, be sure to ask questions in class when I take questions on these notes. Okay, so let's define something real quick, which we've already talked about. And you could probably complete this definition on your own. See, if I say, look, if the limit as x approaches a of f of x equals to L, what am I basically telling you? I'm telling you that the two-sided limit exists, which means if I approach a from the right side of f of x, that'll be L, and if I approach a from its left side, f of x will also go to L. So this is an if and only if statement. So we could say, look, if the limit as x approaches a of f of x equals to L, that's true if and only if the limit as x approaches a from the left side of f of x equals to L, and the limit as x approaches a from the right side of f of x equals to L. So it's kind of like saying, look, if this is true and this is true, then the two-sided limit exists. Okay, so it's kind of like what we've been talking about all along. Okay, so the last thing we're going to talk about has to do with infinite limits. And an infinite limit is what we did for example 1. If you notice in example 1, if you want to go back to it and look at it, we said what happened to our function, which was, I believe, right here. Where was it? It was actually right here. What happened to this guy as x got close to 5? And what we notice is the y values went to infinity and negative infinity. So that's what infinite limits are. So infinite limits are those limits that are going to go to, your function is going to go to infinity or negative infinity. So I guess the question is, if a function goes to infinity, does that exist? Yes or no? And that's actually something to think about. And the answer to that is it doesn't. So one fact we want to make here is that, look, infinite limits are limits that do not exist. Okay, that's very important. So if you say, oh yeah, my limit does exist, it's infinity, that's probably like a cardinal sin. Okay, that's like the biggest, the most illegal move you could ever make when you make that kind of a claim. Because if we go back to the definition of a limit, what is it that we said? If a limit exists, what is it that we're saying? Limit as x approaches a of f of x, that's equal to L, right? So L is actually a number, right? So if you tell me that the limit exists and it's infinity, then my question to you would be, what number is infinity? I mean, it's not a number, right? We can't really assign a number to it. Infinity is, it's a non-existent number. It's something that gets larger and larger and larger. So it's not a number. It's not settling down to a number. So anytime you say this limit is infinity, or when you define a limit and you call it infinity, in other words, you're saying it does not exist. Okay. However, there's a big difference between the two. Or there's actually an important way of expressing these limits, and we'll talk about that right now. So let's look at another example. Okay, if I said find the limit as x approaches 0 of 1 over x squared. Okay, so what you notice is we can make a table again, and if I plug in, for example, 1 or plus or minus, because the good news is when you square it, so I'm approaching 0 from both sides. So I'm going to do plus or minus because I'm going to take 1 is to the right, 1 is to the left. If I plug in plus or minus 1 here, I get the same output. I get 1. If I plug in plus or minus 0.01, I get 100. If I plug in plus or minus 0.001, I get 1,000. And so what is it that we're noticing? As I approach 0 from the right side, we could say as we get closer to 0 from both sides of 0, notice how from the left and the right they both go up to infinity. We could say 1 over x squared goes to infinity. So what does that mean? So we could say the limit as x approaches 0 from both sides of 1 over x squared equals to infinity, which, by the way, I'm not saying that this limit exists. This is another way of saying it does not exist, okay? But I expect you to say it this way. How come? Because it helps me visualize it. Here's what I know. If you tell me that as x approaches 0 from both sides of 0 of 1 over x squared, which is infinity, which in other words is saying does not exist, I could visualize it and say, oh, I get what you're saying. If I approach 0 from the left side, it goes up forever, and from the right side, it goes up forever. So it helps me visualize it, okay? Whereas if you look at the first example we talked about, which we said, or another example we could do is I could say, what would the limit as x approaches 0 from the right side of 1 over x? See, I can't call this infinity or negative infinity because they don't agree from both sides. If you look at this, the graph of it looks like that. So notice how from the right side of 0, it goes up to infinity. From the left side, it goes down to negative infinity. So I can't say this is infinity or negative infinity because they don't agree. So this is when I would say does not exist. So do you guys see the difference between this one and this one? They're both non-existent limit, but what do I know? When you say this one does not exist, I visualize that from one side, it's going to go up to infinity or it's going to go somewhere else. And then from the other, it's going to do something different, okay? Whereas this one, from both sides, it goes up to infinity, so I could visualize it better. I'm saying, look, from both sides, it can go up forever, okay? So before we finish this up, let me give you one more definition, and then we'll do one more big example, and then that will wrap up the notes. So I'm defining basically what an infinite limit is. So we would say let f be a function defined on both sides of A except possibly at A itself. Okay, so think of it this way. what am I saying here? Or why don't we care that it's defined, if it's defined at a or not? Because remember, we don't care what happens to the function at a. I want to know what happens to my function as I get close to a. Okay, so as long as I'm near a, my y values exist, I'm good. I don't care what it is at a. It could be defined at a or undefined, or who cares? Who cares what it is? Okay, so here's what we could say. Then the limit as x approaches a of f of x equals to infinity. What does this mean? It means that the values of f of x will be arbitrarily large by taking x sufficiently close to a. And maybe in parentheses, I should say from both sides of a. Of course, but not equal to a. So all this is saying is, if you put the limit as x approaches a of f of x equals to infinity, this is saying as you approach a from both sides of a, f of x is just going to get larger and larger and larger and larger, except we'll never get to a. So we're never going to hit a. We'll never equal to a. So whether it exists at a or not, we could care less. Okay. So that's what this means. And by the way, once again, this limit, is it existent or non-existent? And the answer is, well, anytime you say the limit as x approaches a of f of x equals to infinity, I like to in parentheses put does not exist, just to acknowledge that, look, I'm still telling you that this limit does not exist. So infinite limits are non-existent limits. Okay, so let's look at this next graph. So I'm going to create a graph here, and I'm going to ask you guys to find certain limits. So let's call this, let's put a vertical asymptote there. Let's call that x value A. Let's call this x value B. Let's put another vertical asymptote here, and let's call that x value C. And let's put another vertical asymptote here. Let's call it D. Okay, and hopefully this one example will help us kind of put together everything we've done for the notes here. So if I have a function that looks like this side does that, and then goes up here. At B, we have an open point, and then it goes down. And let's call the y value at that open point, let's call that L. And then at C, we have something like that. And finally, I have something like this. Okay, so here's what I want you to find, the following. And once again, you're probably better off pausing this and trying to answer these yourself, and then playing it again and seeing what your solution is. So the first thing I want to find is limit as x approaches a of f of x, then the limit as x approaches a from the left side of f of x, and then the limit as x approaches a from the right side of f of x, and then the limit as x approaches b of f of x, and then find the limit as x approaches c from the right side of f of x, and then the limit as x approaches c from the left side of f of x, and finally the limit as x approaches c of f of x. So once again, take a minute, pause it, and see if you could answer these just by looking at the function, and then we can you could press play and we could talk about it. Okay, so now let's look at what happens here. So the limit as x approaches a from both sides of a of f of x. Let's see what happens. As I approach a from the left side, this goes to negative infinity. Okay, and right away, since it's infinite, I know it doesn't exist, but what type of a non-existent limit is it? So now, if I go to the right of a, I see that it goes, as I approach a from the right, it goes up to infinity. So from the left side goes down to negative infinity. From the right side, it goes up to infinity. And so what do I notice? They don't agree from both sides, which means for this, I'm going to say does not exist. Okay? So if you remember, there's three ways we could say a limit does not exist. One is by DNE. The other one is positive infinity. The other one is negative infinity. So let's look at what happens here. If I approach A from the left side, we already talked about this. As I approach A from the left side, it goes down forever, which means it goes to negative infinity, which in other words, I'm also saying the same thing as what? It does not exist, except I'm being more specific because it's easier for us to visualize. This says, look, if you get to A from the left, close to A from the left side, my graph is going to go down forever. So for visual purposes, it's very important that you put infinity and negative infinity. And I expect you to do that on the test as well. Now, what if I approach A from the right side? You can see that it goes up to positive infinity, which in other words, it's still saying it does not exist. Okay, so you could, in parentheses, put does not exist, which is doing the same thing. Now, what's the limit as x approaches B? Now, if I approach B from both sides, from the left side it approaches L, from the right side it approaches L. So notice how from both sides it agrees, although it's not defined at B. Once again, I don't care if it's defined at B or not. I just want to know, does it approach a y value from both sides of B as I get close to B? And the answer is yes, it gets closer and closer to L. So this one is actually L. Now, what if I'm approaching C from the right side? If x is approaching C from the right side, this goes to negative infinity, so it goes down forever. So this is also negative infinity, which does not exist. If I approach C from the left side, notice how this goes down forever as well, which is also negative infinity, which in other words we're saying does not exist. Now the two-sided, here's how this is different than limit as x goes to A. From both sides of C, they both agree that it goes down to negative infinity from both sides, which means it's negative infinity, or in other words, it still means does not exist. Now look, why could I say negative infinity here and I couldn't say negative infinity or infinity here? It's because for this one, from both sides, they don't agree. They do kind of like the opposite, but here from both sides, they're doing the same thing. So remember, these are still both non-existent, but this is more specific, okay? So that basically wraps up section 2.2. You should now be able to answer your questions on these limit problems. And, please come to class with questions if you have any, okay?